Introduction to Linear Approximation and Differentials. So the goals here, understand how to create and use the linear approximation function, which we're going to see is just really an expansion of the tangent line concept. We've already been making tangent line equations. We're just going to see it used in a slightly different way here. And then we're going to look at understanding differentials. And differentials are just a different way of looking at dy dx equals f prime of x. And specifically, the focus is going to be more on the dy and the dx aspect. They're going to be these differentials, so to speak. The change in y, the change in x. And they'll be based on the derivative-derived tangent line. So that's why they kind of put them both together here in the same section. So linear approximation. First thing to recall, tangent lines to curves can be created by starting with the point-slope form of a line. So you get this y minus y1 equals m times x minus x1. And at a given x value, x equals a, let's say, you can use f of a for the y1. And you can use f prime of a for the slope m. Your derivatives give you slopes, so we can just use that for the m. And if you use those, you can obtain the equation of the tangent line to the curve at x equals a. So you get this y minus f of a equals f prime of a times x minus a. And you've already been doing this. So one thing to note is that the tangent line equation can also be used to estimate function values near x equals a. And visually, what this looks like, something like this. So you have some curve like so. You got a tangent line. Let's see, we're going like about right there. So you got your f of x curve here. You got your a here. And notice that the tangent line in what they would call a neighborhood around A does a pretty good job of giving you y values that are close to what the f of x curve's y values would be. So, as you go farther away, of course, the worse it's going to be. If you're targeting at A here and then you're using your tangent line to approximate values way over here, you got quite a gap here. So you don't want to stray too far away from A. And depending on the function, it's relative, so to speak. Further away, is a relative concept. Sometimes you got to stay really close to A. Sometimes you can go really far away, depending on how much change is actually happening in the f of x at that A value and around that A value. But mathematicians realize that, this tangent line can actually be used to approximate function values, and they just basically rebranded the tangent line equation as the linear approximation equation by making a slight adjustment. So, we start out with this y minus f of a equals f prime of a times a quantity x minus a. And then I'm going to solve for y, so we get y equals f prime of a times quantity x minus a, and then plus f of a, adding that f of a to both sides to get y alone. And brace yourselves, this is where all the magic happens. We are now going to create the linear approximation equation, or more importantly, a function that we can use by just saying, y is going to be L of x. Everything else stays the same. So this is really not, some earth-shattering change of the tangent line equation. It's just a matter of saying, hey, we're now going to use this for this special thing. We're going to use it to approximate values. So we call it the L of x function, the linear approximation function, and it's all just based on the tangent line equation. So let's go ahead and see this in an example. We're going to find L of x for f of x equals the square root of x at x equals 4. And then we're going to use L of x to approximate the value of the square root of 4.3. So first thing, I'm going to just start building up this formula here. And I'll start out with the f of a. And note in this case that the a is 4. So I'm going to find f of 4. And that'll just be the square root of 4, which is 2. So I got one part of it. And then I'm going to build up f prime of x first, and then I'll find f prime of 4. So f prime of x is the derivative with respect to x of the square root of x. And that's really the derivative with respect to x of x to the 1/2. And using the power rule, doing a little simplifying, you would get 1 over 2 square root of x. So then f prime of 4 is just going to be 1 over this quantity 2 times the square root of 4. And when you work that out, you get 1 over 4. So now I have the two big pieces I need along with the a to create my L of x equation. So L of x equals 1/4 for the slope times x minus 4 and then plus 2. And you could expand that out, simplify it, but that is a perfectly acceptable L of x linear approximation function. And then I'm going to go ahead and figure out the approximate value of the square root of 4.3 by simply just plugging in 4.3 into that linear approximation function that we created. So we get this 1/4, 4.3 minus 4 in the quantity, and then plus 2. And when you work that out, you get 2.075, which if you were to put in your calculator square root of 4.3, you would see 2.075 is not a terrible approximation. And that's about all there is to that linear approximation. It's just a different way of using the tangent line equation, and they just use that L of x notation now instead of calling it a tangent line. Okay, so let's take a look then at differentials. So differentials, they're a related concept to linear approximation, and it uses a slightly different way of thinking about the fact that dy dx is equal to the f prime of x. So let's look at a visual to get an idea of how this concept works. There's going to be a lot going on in this visual, so I'm going to try and draw this nice. And get this kind of going like so. I just seem to like that same basic curve shape there. So we got that f of x. And then I'm going to try and go through that point there with the tangent line, because differentials are still going to be based off of a derivative-based tangent line idea. And let's go ahead and call this point there where the line is tangent to the curve the x1. We'll just call that the x1 location. And if this tangent line, if this is the L of x line, what we really have here is that f of x1 and the L of x1 are the same. They share that tangent point, that point where the line is tangent to the curve. And then I'm going to go a little further away. I'm going to put this x2 here, and then I'm going to go up, and there's a point here on the L of x, and then another point here on the f of x. And for the L of x, we get this L of x2 here, and then for the f of x, we have the f of x2 here. So we can see that there is a difference between the linear approximation value and the true function value. And let's start kind of putting that into terms of some notation. So for the x1 to x2, I'm going to start saying that, okay, in between these two, there's a certain change in the x. And the true change in the x is delta x. That's the notation they use. A little triangle, delta, stands for change in. And then if I look here at my, and you're going to want to draw this over a little further, kind of like what I'm doing, because I'm going to put something else inside of there. But looking at the true change in y between the original point and the second point, we get this delta y. Okay, so that's all based on what we're looking at with the true f of x, the true change in y. Now, for the linearization, which is based on derivatives, which is based on that f prime of x giving me the slope, and thinking about the dy dx now as a in a sense, a differential, a derivative-based change, we could say that the change in the x's, well, there's no difference between the delta x and the dx. If I change the same amount, whether it was on the original function or the L of x, the x's change the same. However, on the derivative-based L of x, the dy is different than the delta y. So this differential dy is just an approximation of the delta y. So what we're going to see here then, the actual change of the function value, notated as this delta y, between x1 and x2, can be found by just evaluating the change in the function values. And the first function value we would have is, or I should say the second technically, because you want to do the bigger one minus the smaller one, but we would do this f of x plus delta x. So in general, not using x1, x2, we're just using some x value plus a delta x, and then we subtract away the f of x. And in this way, by doing the x plus delta x evaluation first, subtracting away the f of x, if the slope happened to be negative, it would be, if the change in y was negative, we would see that represented. So then the differential dy can be used to approximate that actual change. So in other words, delta y is approximately dy, the change in the y on that differential, that derivative-based linear approximation line. So since the differential is based on the derivative, oops, I wanted to write this down here. Now that linear approximation line, you can't get it without having the derivative. We can think of things in this way. So we got this dy dx equals f prime of x. And we're now going to treat the dy as its own thing, this change in y based on the derivative. So we're going to have this dy just equals f prime of x times dx. And this is the differential equation that relates dy and dx that we'll be using moving forward. So for this next example, we're going to let y equal cube root of x. And I want to find the differential dy. Well, dy equals f prime of x dx. And the f prime of x, if you were to think of this cube root of x as being x to the 1/3, you work out that derivative using the power rule, you're going to get 1 over 3x to the 2/3 power, and then times dx. So the f prime of x is here, and then we multiply that by the change in x in order to get our differential base change in y. So for part B, and I only get 15 minutes on this video, so I'm going to put this part B into a very short part 2.